Throughout your math career, you've learned how to solve many different types of equations. Linear, quadratic, cubic, degree 4, exponential, logarithmic. Now we want to look at how can I solve a trigonometric equation. So we're going to look at it in two different parts. The first part's going to be in video. The second part will be an in-class lecture. On the videos, we're always going to be given an interval. So to solve a trig equation, what we're going to always want to try to do is we want to try to get the trig expression by itself. We want to try to isolate it. Then we can use inverse trig functions to solve for the variable. Oftentimes we'll skip that step and we'll just kind of go right to our unit circle and ask ourselves what rotation gave us that value. But when we do that, we are using essentially a trig inverse function. Oftentimes we're going to find our first two solutions, so then we can move on to find the general solution. But this we're going to do, that's going to be that in-class piece. Also, just to keep in mind, and we'll see some more of this in class as well, we also have to make sure to remember different things that different techniques we've learned in other math courses, such as factoring or quadratic formula, to assist us in solving that for that trig expression, or using some identities we've learned in this unit. So let's go ahead. We have 4 examples here. In the first example, first thing I want to do is I want to try to isolate that trig expression. So if I think of this in the same way I would think of a linear equation, if I had 4x equals 2x plus radical 2, and I was trying to solve for x, hopefully you would agree with me that the first step would be to combine my x's. Well, I'm going to think in that same way with my trig functions. The first thing I'm going to do is combine my signs. So I'll subtract 2 from each side, giving me 2 sine of x equals radical 2. Again, I haven't quite isolated the trig expression yet, but I've gotten closer to that. I can get it by itself by dividing both sides by 2, giving me sine of x, so sine of some rotation, is radical 2 over 2. Well, how do I solve for that rotation? I take the sine inverse of both sides. So I notice that radical 2 over 2 is on my unit circle. So when I do that, I get what rotation, because the inverse functions give me a rotation, I'm looking for the rotation that gives me values in this interval. And I want to give an exact answer, and my calculator, if I put this in, is only going to give me my reference angle. So I'm going to use my unit circle to make sure I get all of my values. So I look on my unit circle and I see that at x equals pi over 4, so at a rotation of pi over 4, my y value is radical 2 over 2, as well as at x equals 3 pi over 4. So those are going to be my two solutions in my given interval. Example 2 is very similar to example 1. So what I'm going to do is I'm going to move on and do examples 3 and 4. Then I'm going to come back and do example 2. And that way, if you understand what I'm doing and you don't want to go through example 2, you can go ahead and stop the video after example 4. So I'm going to bump ahead. So example 3, notice I already have the trig function by itself. I already have my cosecant value on one side alone. The problem is that I don't have cosecant values on my unit circle. So rather than use my calculator to take the inverse, and I'm not even sure if my calculator has a cosecant inverse button on it, I'm going to go ahead and say if cosecant equals 2, that means that sine, because it's the reciprocal of cosecant, must equal 1/2. And I recognize 1/2 as a value on my unit circle. So I go to my unit circle and I ask myself for what rotation, so sine of what rotation, gives me a y value of 1/2. Well, I notice I get a y value of 1/2 at a rotation of pi over 6, as well as a rotation of 11 pi over 6. And that is going to be it. That's my answer. That one's fairly simple as long as you realize that cosecant needs to be written in terms of sine. It would work the same way with secant. Moving on to example 4. So example 4, I have 3 cotangent squared of x plus 4 equals 7. Well, again, if I thought of this as a linear function, if I had 3x squared plus 4 equals 7, I would know I had to isolate that x squared so I could take the square root of both sides. I would do that by subtracting a 4 and dividing a 3. Well, that's exactly what I'm going to do here with my trig function, giving me 3 cotangent squared x equals 3. Dividing by 3 leaves me with cotangent squared x equals 1. So now I'm going to go ahead and take the square root, and when I do, I'm left with cotangent of x equals plus or minus, I can't forget that, the square root of 1, which is just plus or minus 1. So I'm going to ask myself, when does cosine of x divided by sine of x equal either positive or negative 1? Well, that means cosine and sine either have to be the same value or opposite values. And I notice that happens a total of 4 times within this interval. It happens at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. If these examples made sense, you can go ahead and stop the video now. If you'd like to see another example, I'm going to go back now and do example 2. So example 2 is very similar to example 1 in the aspect that I have cosine of x appearing more than once, which means I can go ahead and combine those like terms. So I'm going to move the 3 cosine of x over, giving me 2 cosine of x equals radical 3. And then I'm going to go ahead and divide by that 2, giving me cosine of x equals square root of 3 over 2. So again, I'm going to ask myself, cosine of what rotation gives me a value of radical 3 over 2? Looking at my unit circle, I see that a rotation of pi over 6 gives me an x value of radical 3 over 2, as well as, sorry about my dog, as well as a rotation of 5 pi over 6. So those are going to be my 2 solutions within this interval. So I'm going to go ahead and stop the video here. If you have any questions, please bring them with you to class.